Okay, so finally what we have after the primary hemostasia is that we have reached to this platelet clot. Once it is produced, then we need to stabilize and get a more strong clot that is maybe due to the secondary hemostasia. The secondary hemostasia, we said that it is divided in two pathways, the extrinsic pathway and the intrinsic pathway. Both go to a combined common pathway to finally produce this clot. So we have said that we for the secondary hemostasia we have this extrinsic and intrinsic pathway. It doesn't mean that depending on the stimulus we are going to one or another. Usually in the in clinical practice, what we have is that we have an event, either a bleeding event or arteriothrombotic events. Both pathways are involved. The splitting this in these two pathways is because of research. Because when research started, they showed that the extrinsic pathway was one pathway that we can trigger it by what is called the tissue factor, that is an organic substance that is in the vessels, and the intrinsic pathway do not need this tissue factor to start. But as we will see, both are involved. It doesn't depend whether it's triggered by an injury or atherothrombotic event. Both pathways will be involved because the extrinsic pathway by itself is only capable to produce a very weak clot, and we need 90 to 95% of the function that is provided by the intrinsic pathway. So we will go step by step. Then we are going to start with the extrinsic pathway. We call it extrinsic because for the initiation of this cascade through this way, we need tissue factor. We got that when we got this injury in the vessel, the blood get in contact with fibroblasts and also with fibroblasts and smooth muscle cells. Inside these cells, we have that is the tissue factor. This tissue factor is coagulant factor number 3. Okay, so when it gets in contact with another coagulation factor that is number 7, it gets activated. We also need for this activation two things that are very important in the coagulations, that are both calcium and phospholipids. Calcium and phospholipids are very important for the production of the clot, mainly because calcium allows to the different cells to stick one to the other. Why? Because usually, take for example this platelet, usually the platelets and other cells have negative charge inside of the membrane. When the cell gets activated, then it goes a phenomenon that is the flip-flop phenomenon, where those negative charges goes outside. And if we have another cell here with negative charges, we need a positive charge in the middle to be able to join these cells. And in that case, this positive charge is usually calcium. That's why calcium is very important in the coagulation. So after that, when we have this activated tissue factor, then it will activate factor 10. Factor 10, up to now, here's the end of the extrinsic pathway, and here it begins what is called the combined pathway. Then this factor 10 will become in activated factor 10. Then this activated factor 10 will activate factor 2. Factor 2 is called prothrombin. It will turn into activated factor 2 that is called thrombin. This thrombin is very important because it's the core. As you will see, a lot of arrows are going into and out of thrombin, because thrombin is considered like the core of the coagulation cascade of the secondary hemostasia. This thrombin will activate factor 1. Factor 1 is fibrinogen. Remember the fibrinogen that we have in the primary hemostasia? Okay.
Yeah, we have fibrinogen.
It will turn into activated factor 1 that is called fibrin. But this fibrin is only monomers, so they are isolated monomers of fibrin. So they become aggregated and they start forming strands, so they get the fibrin mesh. So, in order to stabilize this fibrin mesh, we got that the thrombin, factor 2, activates factor 13. We have factor 13 that becomes activated by thrombin, and we got activated factor 13. This activated factor 13 really stabilizes the fibrin mesh and allows the proper aggregation. So up to now we have this extrinsic pathway, and then we have the other one that is the combined pathway to get finally to the fibrin mesh. But we have said that we have another pathway that is the intrinsic pathway. Which things can trigger this intrinsic pathway? Well, this exposed collagen, also the platelets, and also the basal membrane. That is below the endothelium. All of them can start. In that case, the coagulation factor that will be activated is factor 12. Factor 12 gets activated and turns into factor 12 activated. This factor 12 also through the kallikrein pathway is able to release bradykinin. Those bradykinins are able to produce vasodilation, are able to increase permeability, produce pain. So through this pathway we get the swelling when we got an injury. Okay, after that we continue with the coagulation cascade. We will have that this activated factor 12 will activate factor 11. And this factor 11 will activate factor 9. Okay, finally we have this factor 9 that is already activated. This one is the one that is able also to get into the combined pathway and activate this factor 10 and then get into the fibrin mesh finally. But we got that this factor 9 is able to activate factor 10 but in a very weakly way. So, okay, there are another two important coagulation factors that are very related to platelets. Why? Because they are usually traveling not only along the blood flow, they are also sometimes attached to the surface of the platelets. Those are factor 8 and factor 5. Those two factors are usually activated by thrombin, by factor 10. That's why we said that thrombin is very important. So we are going to have on one side what is factor 8 that needs to stick with von Willebrand factor to be activated, but also needs thrombin to become into factor 8 activated. Okay, so this factor 8 activated promotes the activation of factor 10 due to factor 9 a lot. It multiplies by more than 200 times, so makes it more efficient the activation of factor 10 through this pathway. We have said that there is another factor that is factor 5. Factor 5 can also be activated by this factor 2, and activated factor 5 does the same with the relation of the activation of factor 10 with factor 2. So in the end we can see that there are a lot of feedbacks in which factor 2 or thrombin is involved, and it makes them, when we add the intrinsic pathway to the coagulation, we get a much bigger clot. That's why extrinsic pathway is only 5 to 10% of the clot, and intrinsic pathway with all the feedbacks gets like 90-95% of the clot. Okay, so far we have covered all the primary hemostasia, all the secondary hemostasia, to the form of finally the strong fibrous mesh. But if we only had that, we will have a big propensity of the body to form clots. Then we need other things to counterbalance. So the body has one system, that is the physiological anticoagulation system, that tries to counterbalance all the things that we have seen so far. So the anticoagulation system has several issues. One of them is the system that is formed by protein S and protein C. We could say what happens is that protein S activates protein C, and the activated protein C inhibits both factor 8 and factor 5. That's why the system by protein S and protein C have anticoagulant effects, and mutations in those proteins can lead to prothrombotic events. On the other side, we have another system that is the one that is formed by antithrombin. The antithrombin 3, what does is that it inhibits both mainly this factor 10 and factor 2, but also the other factors of the intrinsic pathway. It will also inhibit factor 9, factor 11, factor 12. This antithrombin system is very related to the functions of heparins that we will see later. And finally, we have another one that is the tissue factor plasmatic inhibitor that acts in here. So by those anticoagulant physiological pathways, the body avoids the formations or the excessive formation of clots. But there is another system, that is the thrombolytic or fibrinolytic system, that, like in a physiological way, the body tries to breaks the clots. This fibrinolytic system is mainly due to one substance, that is the plasminogen, that can be turned into plasmin by one substance, that is the tissue plasminogen activator. This plasmin can act in this fibrin mesh and can lead to fibrin degradation products. That is like a physiological way of the body to try to break the clots.